Гешева на тему MPLS Security. Поприветствуем его.
Hello everyone. First of all, really sorry for not speaking in Russian, but my Russian's really rusty. I come from Bulgaria and I understand most of the stuff you guys are saying, but I can't really talk in Russian. So I do security research for a company called MWR in the UK, and the talk today will be about pen testing MPLS networks. MPLS is basically a service provider technology that I'll be talking about in details in just a moment. So the agenda for today is a quick overview of what MPLS is, some quick retrospection of some previous MPLS research, and then moving on to the interesting bits of this talk, which is reconnaissance for MPLS networks, introducing VRF hopping, which is an interesting attack for breaking out of MPLS VPNs, and then I'll give some advice on securing and hardening MPLS networks, MPLS environments. And of course, a few ideas on improving this research and probably ideas on building up on that research for the purpose of extending it. So what is MPLS? MPLS is the most widely used mechanism, if you want, technology in service provider networks. It's a layer 2.5 protocol used in telecommunication networks, high-performance telecommunications networks, where the reliability of the communication is kind of critical. Basically, this protocol is designed for the purpose of processing information as fast as possible from point A to point B. And the way it works is by looking up labels as opposed to looking up destination IP addresses. And that's where the efficiency comes from, because the structure of an MPLS label is a lot less complicated compared to a destination IP address. And the process of looking up a label in a label information base is a lot less complicated compared to looking up a destination address in a routing table. So that's the main difference. There is only a single longest prefix match when the traffic is handled at the edge of the MPLS network, and from there on, the only transition is based on looking up label values. So a lot of providers, they build VPN services on top of MPLS. These are layer 3 services or layer 2 services. In this talk, I'll be reviewing layer 3 architectures. So there is a few things I need to mention before proceeding with the actual content. These are terms that I'll be using throughout the talk. You don't have to remember all of these, but, excuse me, you have to understand some basics about how MPLS functions and what are the devices involved in an MPLS process. So I already mentioned MPLS works with labels. There's 3 operations defined for these labels: pushing labels on a stack, popping labels off a stack, and swapping labels on the stack. These labels are 20-bit values, and the first 1 to 16 labels are reserved for special purposes. I'll be probably mentioning some of these in a bit. Devices that process MPLS traffic are called label switching routers or LSOs. The provider router is a router that stands somewhere within the core of the network, processing pure MPLS traffic. Label edge router is an MPLS-enabled service provider device that processes MPLS traffic, but also handles the ingress customer traffic, translating IP traffic into MPLS traffic. This one is also called provider edge device. And there is the label switch path, which is the logical circuit from one end of the MPLS network to the other end of the MPLS network. And it kind of defines a virtual tunnel where the customer traffic would flow. A customer edge device is the customer device connecting to the service provider infrastructure. So it's basically the last device from the customer side connecting to the provider edge rather. Now I need to introduce another term called virtual routing and forwarding. Virtual routing and forwarding allows multiple instances of a routing table to exist and operate at the same time on the same device. So if you know about VLANs, you can think about a VRF as the equivalent of a VLAN on layer 3. You can have separate routers, basically separate virtual instances of a router running on top of the same physical router. One thing to mention and to remember is that VRFs are only locally significant to the device where these are configured. So this is a really basic example of what an MPLS network would look like. You see the customer edge device, as I mentioned, that's the device connecting the customer to the provider. This customer edge device connecting to the provider edge device from the service provider side. Within the MPLS network, you have MPLS routers processing pure MPLS traffic. These are called core MPLS devices or just provider edge devices. On the other side of the scheme, you have the exactly same equivalent. A few more words on MPLS. What does an MPLS header look like and where this header sits? So MPLS, as I said, works with processing labels. These labels are stored, this information about the labels is stored in a equivalent of a routing table called label information base. And of course, a lookup in the label information base would give you a destination for the LSP according to the label and the destination you're processing for. MPLS encapsulation, how does this work? So basically at the edge of the network, you see the provider edge device, it receives IP traffic. This IP traffic needs to be encapsulated in MPLS before it is processed further within the MPLS network. So at the edge of this network, the provider edge device will take the IP traffic, stick an MPLS header in between the Ethernet header and the IP header, and that's why the MPLS protocol is called a layer 2.5 protocol. The interesting thing is, I already mentioned you have 3 operations for the labels, pushing, popping, and swapping, and that's because you can have multiple MPLS headers sticked on top of each other. So you can imagine you can have 3 or 4 MPLS headers depending on the complexity of the network and the traffic engineering strategies for the service provider. That's what an MPLS header looks like. I already mentioned the label field is 20 bits field. It's an integer value. The experimental field, as far as I know, as far as I can remember, is not being used at the moment. I don't think I'll perform the demos anyway. Yeah. No, I'm not doing it because it will take way too long for my software to boot. Okay. That's fine. The experimental field not being used, as I said, at the bottom of the label stack means whether this is the bottom MPLS header in the series of MPLS headers, if there's more than one of those. And the TTL is exactly the equivalent of the TTL in an IP header. It is used for preventing loops within the network. So a little bit of retrospection, a little bit about some MPLS research performed in the past. The most notable research that I would like to mention is the one from InnoRay from ER&W from 2006. Another really good piece of research is MPLS security overview from Thorsten Fischer from IRM 1 year later. And just recently, there is a nice, interesting blog from Portcullis Labs about the basics of pen testing MPLS networks. So what is common for most of these pieces of research is that they assume that there must be a misconfiguration in the service provider network to perform most of the critical attacks. So they assume that either there is a misconfiguration or that an attacker is able to already get access to the core of the network. So if you're an attacker and you have access to the MPLS core, it's pretty much game over, because from the MPLS core you can manipulate labels, you can jump via VPNs, and you can kind of mess with traffic engineering strategies in the network. So that's the most common thing for these pieces of research so far. I'm going to start with MPLS reconnaissance. Imagine that you're a client or performing a pen test for an MPLS provider. The most basic thing that you can do right at the beginning is reconnaissance based on the physical connectivity to the service provider device. That is, you have layer 2 connectivity, and based on this layer 2 connectivity, you can get information such as the MAC address of the remote system. Based on that, you can kind of get an idea about the vendor of the system sitting between you and the MPLS network, which may be useful. Packet capturing may be useful because a lot of providers forget to kind of filter management protocols such as LLDP, CDP, and MNDP. These are layer 2 protocols used for advertising a lot of useful information to an attacker. So, for example, LLDP used by Huawei, HP, Juniper, and other providers. CDP is another one from Cisco, a proprietary one. MNDP is another one from MikroTik, as far as I can remember. And all of these protocols, they advertise a bunch of data related to the system, such as the operating system version, the firmware version, the firmware revision, the number of interfaces on this system, and in certain cases, some configuration specifics related to this system. So by default, most of these devices, they would advertise this freely on every single interface. And if the service provider forgets to kind of filter this sort of traffic, you can easily get this information for free. In certain cases, a lot less often, I would say, you may get misconfigured service provider devices advertising routing protocol information onto the customer interface. So basically, a service provider trying to establish an OSPF session with a customer without even realizing it. So as I said, a lot less often, but you may still see that. And the last one, and I guess the most obvious one, is to perform a port scan on the service provider device that you're directly connected to, and you can get information about the running services on that. So according to these RFC code, security of BGP, MPLS, IP VPNs, it is recommended for the service provider as well for the customers to kind of hide and obscure the structure of the MPLS network. So basically, if I'm an MPLS customer, let me see if I have my diagram. If I'm an MPLS customer on client side A and client side B, basically having 2 remote offices, and I want secure connectivity between these 2 offices, when I send traffic from office A to office B, I shouldn't be able to reveal any details about the interconnections in the service provider network. Basically, I should have no idea about the number of intermediate devices, the IP addresses of these devices, and the label information used for forwarding this traffic. So basically, this RFC tells you that you should be able to hide your network, and you should do that as part of the security best practices. How is this thing achieved in MPLS networks? There are 2 mechanisms, one of them called IPTTL propagation, the other one called ICMP tunneling. IPTTL propagation is the process of taking IP traffic, IP packets, copying the TTL into decrementing the TTL as copied from the IP header and sticking it into an MPLS header. So basically, at the edge of the network, the provider edge device takes the packet, processes the IP header, and takes the TTL. This is enabled by default for most of the vendors, if not for all of them. And propagating the TTL means that an attacker may be able to reveal the number of intermediate devices by manipulating the TTL value. We'll see that in a bit. ICMP tunneling is another one. So imagine, again, let's get to the diagram. I'm trace routing from customer side A to customer side B. If there is an ICMP error message generated along the LSP, along the path between my office A and my office B, this ICMP error message needs to be routed back to me. But the core MPLS devices would have no idea about routing this ICMP error message back to my originating point because of the lack of routing information. Remember that the core devices would only process data and traffic based on the labels. So imagine there's a TTL time exceeded generated somewhere in the service provider network. This ICMP error message needs to be forwarded all the way to the far end of the VRF, to the far end of the MPLS network, to the provider edge device before it gets routed back to the originating point. So that's the purpose of ICMP tunneling. If there is no ICMP tunneling, there is no way for an MPLS device to get the error message back to the client. So this is the sample MPLS topology that I'll be using for most of the examples, and unfortunately not for the demos because I won't be able to do them. You have a customer with 2 remote offices connected via an MPLS layer 3 VPN, and there's 1 core device and 2 provider edges. So let's say ICMP tunneling is enabled and IPTTL propagation is enabled as well. This means that I am able to force a provider edge device to use a specific TTL, and this TTL would eventually expire somewhere within the MPLS network. When this TTL expires, there is an ICMP TTL time exceeded message generated, and this TTL and this ICMP message is routed back to me because of the ICMP tunneling being enabled. So in this case, in an insecure configuration, you can reveal the IP addresses for the internal network as well as the MPLS labels used within the MPLS network. In a nutshell, to have a secure configuration, you need to disable TTL propagation and you need to disable ICMP tunneling. You need to disable IPTTL propagation at the edge of the network because that's where the TTL propagation happens, and you need to disable ICMP tunneling all along the LSP. So basically, every single MPLS device should have ICMP tunneling disabled. Now, let's consider a secure scenario where ICMP tunneling is disabled and TTL propagation, IPTTL propagation is disabled as well. So the first and most basic question is, how would I know about the number of intermediate devices between my customer side A and customer side B? That's not really useful information, but it's a good start for us. So a basic enumeration technique may reveal the number of these devices. This consists of pre-encapsulating ICMP echo requests in MPLS using sequentially incrementing TTLs. Again, this applies only to a few vendors that I've been able to test. A certain amount of vendors were unaffected by this particular technique. The prerequisite for this attack to work is for a provider edge device to process MPLS traffic received on an IP interface. Now, this may be either because of a misconfiguration or because of a faulty implementation. Excuse me. So that's the way we craft the packets. Imagine I'm executing this commands. This is output from Scapy. Imagine I'm executing these commands from client-side A device. First of all, loading the MPLS module, which is not included by default. Then preparing the Ethernet frame with the source MAC address of the client-side A device and the destination MAC address of the provider edge device. The next layer on top of that is MPLS, in this case using label 0. And for TTL, I'm using range 024. So basically, this will generate 4 packets with sequentially incrementing TTLs. For the IP layer, I use source such as the client-side IP address, and the destination, I use the destination on the other side of the VRF, which is client-side B. And on top of IP, I stick an ICMP echo request. I guess this would work with pretty much any protocol, for example, TCP or UDP. So the output from this is roughly about that. You can see that these are 4 MPLS packets, 4 MPLS datagrams being sent, and for the first 3 of those, I get an ICMP time exceeded in transit. So basically this means that if I send a pre-labeled ICMP request with TTL 0, the provider edge device would know the number of intermediate devices, and it would calculate it for me, and it would say 0 wouldn't do the job. So then I can repeat this task with incrementing the TTL, in this case 1, and again, the provider edge device would kindly tell me that this wouldn't work as well. This wouldn't work either. So basically, that's the way I can reveal the number of intermediate devices. As I said, nothing really interesting so far, but it's good to know roughly the size of the service provider network you're dealing with, roughly the size of the MPLS network that sits in between your Office A and your Office B. So the next and I guess most obvious thing to do is to reveal some MPLS service provider devices, IP addresses that are used within the internal network. Again, consider a securely configured device, securely configured network. You have no IPTTL propagation, you have no ICMP tunneling. If you perform a trace route from one side of the VRF to the other side of the VRF, you would only be able to see the IP address of your own gateway and the destination address at the far end of the VRF. Now, this is really sloppy, kind of stupid and non-intuitive. So when I spoke to Eno from ERNW, he was really surprised to see this working, and he was like, wow, I didn't really think about that because it's non-intuitive. It shouldn't work by design. What is this? Is basically sending an ICMP request to the other far end of the VRF, as you can see here. But the only difference is that I enable the IP record route option in the IP header. The IP record route option basically allows the intermediate devices to include their IP addresses in the IP header on the way back from the destination to the source. So basically, every single intermediate device should consider the egress interface, take the IP address of the egress interface for this traffic, and stick it into the IPRR header. The reason this shouldn't work is because MPLS is a layer 2.5 protocol. It's below IP, and the MPLS-enabled devices should not process data above the MPLS layer. I mean, that's the purpose of MPLS, and that's why it is being so efficient in forwarding traffic so fast. Because it would only look up the label information as opposed to looking up the IP header information. And the IP record route option is included in the IP header. So in this case, with a secure configuration, you're able to get 2 IP addresses for the MPLS intermediate devices. Again, I have no idea why this was the case. I had a conversation with some of the guys from the incident response for a few of the affected vendors, and they were like, "Wow, we have no idea why this works. This shouldn't work by design. This shouldn't work by standard. That's how MPLS is supposed to work, not to process IP information on the way from one side of the VRF to the other side of the VRF." So at the moment, the information we have consists of the number of intermediate devices and a couple of IP addresses for these devices. Now, because we know how IP record route option works, it gives us the information that we have the IP addresses for the egress interfaces. So basically, the IP addresses used by the MPLS devices on the way back So when we send traffic, this traffic is being sent back to us, the reply is being sent back to us, and these IP addresses are popped in the IP record route options header, IP record route options field. So one thing we can try is to send IP traffic to any of these intermediate devices. By definition, this should not work because technically we are in an isolated VRF environment that has no overlap with with any other VRF, or in certain cases the management VRF, or you can consider the global routing table as a kind of a default VRF. So basically, we should not be able to send traffic outside of our own VRF. In only one, or I think two of the cases, this was not really true. So basically, once we get the IP addresses 0.1 and 0.6, we can kind of intelligently guess the other side of the connection, because in an MPLS network, most of these connections would be point-to-point connections. And if these are properly configured network devices, they should use a /30 subnet mask, which allows only for 2 valid IP addresses to be used on the network. So we can kind of assume what is the IP address on the other side of the point-to-point link. In this case, we can kind of guess the 2.2 IP address used on the provider edge device towards us. And in this particular case, I can't really say the name of the vendor, but we've been able to send traffic directly to an MPLS-enabled interface, part of the MPLS network. Why is this bad? This is kind of bad because a network administrator, a network engineer, would consider the MPLS network to not be accessible from the outside world. So imagine they have SSH running on the MPLS-enabled devices, but they've been smart enough to filter SSH on the customer interfaces, but still allow SSH within the network itself. So in this case, SSH would not be accessible on the customer-facing interface, but it would still be accessible on the MPLS-enabled interface. So being able to send traffic and receive traffic back from an MPLS-enabled interface is bad for that particular reason. As we saw, there's 2 or 3 kind of so far minor issues with MPLS implementations. I tested about 6 or 7 implementations. One vendor was unaffected. A few vendors were affected by 1 or more of these issues, and 1 vendor was affected by all of these issues. An interesting thing to check is basically perform these tests in a network where there's multiple vendors, basically having a provider edge device from vendor X, provider core device from vendor Y, and another provider edge from vendor Z, let's say. Because I assume results would differ because of the various vulnerabilities affecting various vendors. So that was about MPLS reconnaissance. This was the part where we kind of get and gather as much information as we can about the service provider network without any active attacks, without any interruptions or kind of aggressive, offensive traffic being sent. Now, imagine I mentioned, remember I mentioned VRF hopping. What is VRF actually? Now I need to introduce what VRF hopping is. As I said, VRF, you can think about a VRF as kind of a virtualized network. If you know about VLANs, I assume most of you would be most of you would know about VLANs. So VRF is exactly the equivalent of VLANs on layer 3. You should not be able to break out of your VLAN without using some sort of techniques like double tagging. And it's pretty much similar for VRFs. VRF hopping would mean breaking out of the VRF and sending traffic onto another VRF, pretty much like VLAN hopping. This would allow for either reaching other customers of the network or eventually sending traffic to an MPLS-enabled service provider device, part of a management VRF. So most of the service providers, they would use a specifically configured VRF for accessing their own devices called a management VRF. If there is no management VRF, you can think about the global routing table as the management VRF. How is VRF hopping achieved? Well, this is achieved by pre-labeling MPLS traffic and sending it onto the provider edge, and relying on the fact that a provider edge device would in certain cases process MPLS encapsulated traffic. Sometimes due to misconfigurations, sometimes due to a problematic implementation. What is a potential complication for a VRF hopping attack? Well, that could be the fact that a lot of service providers would use overlapping IP address spaces for their customers. So in this case, there are two customers. Imagine these two customers, they may have the exactly same identical IP address space. Now, for the sake of the example, I'm using separate IP address spaces, non-overlapping address spaces, but it is absolutely possible, and it would be absolutely fine for a service provider and a customer to use overlapping address spaces. So, there's two things we can do with VRF hopping, as I said, attacking MPLS clients or attacking service provider devices. And I'm going to start with attacking MPLS clients. So, as I said, customer traffic is supposed to flow within a dedicated VRF, and different customers' traffic should not mix together. It should flow only within the dedicated VRF. There is no inter-VRF communication by default unless this is explicitly configured via some sort of route leaking. Route leaking means leaking information from one VRF into another VRF, or from the global routing table into a VRF, or from a VRF into the global routing table. But by default, that's not configured. And if you configure a VRF, separate VRFs, these VRFs should stay completely independent without leaking any routes between each other. So attacking other clients means that we'll be basically jumping VPNs or so-called VRFs, and we'll be able to reach other customers' customer edge devices. So this is the example that I'm going to use for what I intended to be a couple of demos, unfortunately not performing them due to some technical issues. So we have customer A who stays within VRF A. We have customer B who stays within VRF B. These are the yellow one and the blue one. Customer A and customer B, they have 2 remote offices each. Customer A's devices are R1 and R2, and customer B devices are R3 and R4. So I'm pretending to be the attacker in VRFA, pretending to be device R1. If I send ICMP echo requests to a device that resides on a different VRF than my own VRF, this should should not reach the remote device, should be discarded right at the edge of the MPLS network. And as we can see, we have 100% packet loss, not receiving anything at all, no ICMP error messages generated whatsoever. So on R4, which again resides in a different VRF, we enable ICMP debugging just so we can see the ICMP messages as they arrive at the provider to customer interface. Then we proceed with crafting packets, again with SCAPI, loading the MPLS module, Ethernet, nothing interesting about it. Then for MPLS, TTL64 or any TTL that would be big enough for traversing the network. And for range, in this case, I use 1,000 to 1,500. Now, this depends on the size of the service provider network, and it also depends on the vendor systems, on the vendor implementation. Some vendors would start assigning labels from 16, which is the first non-reserved label. Some vendors would start assigning labels from 100. Some of them would start from 1,000. So having an idea about the vendors you're dealing with it would only make your life easier, because you can kind of safely assume the range of labels that are valid and configured by default on these devices. So IP source is the source of R1. IP destination is the source of R4. Again, source in one VRF, destination in another VRF. Now, on R4, we can see that 2 out of 500 packets actually reached the destination, basically performing what I call VRF hopping. For some reason, 2 out of these 500 reached the destination. Initially, I assumed only 1 would do that, but further investigating turned out that, revealed that due to misconfiguration issues, we can smuggle more than 1 request. In a properly configured environment, I think the result was only a single packet because of the assignment for the labels. Now, this was VRF hopping performed against clients and performed for the purpose of reaching customer edge devices. As I mentioned, there is also the possibility of attacking service provider devices that reside on the service provider network that is supposed to be kind of invisible and transparent from a customer point of view. And as I said, these are either configured to be part of some sort of management VRF or by default part of the global routing table that you can imagine is some sort of a global VRF. In this case, I already have the IP address for the provider core device, the P device. So if I send ICMP echo request to this device, none of these would eventually reach the destination because these are discarded at the edge of the MPLS network. Now, typing these commands on the P device would enable ICMP debugging and would enable kind of logging on the terminal that I'm currently logged on. Again, performing this exactly same thing, but only changing the destination IP address to the destination IP address of the provider core device. And this would get me, again, 2 ICMP echo requests arriving at the destination and 2 ICMP echo replies generated at the destination. Now, because at the destination, the device would have no information whatsoever about routing this information back to me, these ICMP echo replies would never reach the originating point. In this case, basically, I would have absolutely no idea whether my traffic was successfully delivered to the destination because of the lack of response. Basically, this is the exactly same limitation that you face when you perform VLAN hopping attacks. This may be useful against stateless protocols transported over UDP, such as SNMP or TFTP or universal plug and play, etc., etc. Okay, I'm kind of running out of time. So we saw these are some kind of serious limitations that apply to a classic VRF hopping attack because of the lack of response received at the originating point. What can we do is to consider a couple of scenarios. In this case, a couple of scenarios. One of them relies on a misconfigured, kind of poorly configured customer edge device. The other one relies on a particular network design. Again, kind of poor network design. So the first one is blind C reconfiguration. As you saw, we can send traffic to a customer edge device, but there is no way for us to see the response. So if we have a configuration file for a remote device, let's say in a pen test scenario, and we know that SNMP is enabled on a customer edge device, and this SNMP service is accessible on the customer edge to provider edge link, we should be able to reach the SNMP service, but there would be no way for us to see the SNMP reply. Basically, we can force the remote system to pre-encapsulate its traffic in MPLS before the reply is sent back. How is this done? Well, basically, we define a static route for ourselves, and we defined what is called an MPLS static binding rule. This static binding rule would tell the device that specific traffic, particular traffic, needs to be MPLS pre-encapsulated, sent to the provider edge device, as opposed to being clear IP traffic. The limitations of this, well, first of all, we need to perform SNMP write access community string brute force, and depending on the configuration and the password policies, that may not be applicable. Another complication and limitation is that certain management information bases would have this particular object identifiers as read-only, or would change these object identifiers from version to another version. But the way to perform this is basically the way we did the demonstration for VRF hopping, but instead of having ICMP echo requests, we have SNMP wrapped in UDP, and this SNMP basically tells the remote device that a particular object ID needs to be set to a particular value. And again, brute forcing, generating 500 packets, having fingers crossed, and hoping that our traffic reaches the destination and that we have the right community string. So in this case, you have 500 packets with only one single community string. But if you have a dictionary list, imagine for every single community string, you would have to send 500 packets. So again, not exactly practical, but still getting us somewhere. Now, this scenario relies on kind of a poorly designed client network. Imagine, as a company, I have remote offices. I want the communication between these two offices to be as secure and as reliable as possible. So I go to an MPLS service provider, get an MPLS VPN from Office 1 to Office 2, but for the rest of my traffic, I would still use internet. And this internet connectivity would be completely separate from the MPLS VPN connectivity. Again, design prerequisites, having internet connectivity via separate link. The attack scenario for that is VRF hopping with a spoofed IP address, forcing the victim into generating and sending responses to an internet-facing attack-controlled device. Limitations, again, that's a poor network design decision. It's mitigated by adequately configured traffic filtering policies, and overlapping IP address spaces would cause some serious problems, and not even entirely sure if it's practically possible. So that's the attack scenario for that one. VRF hopping with a spoofed source IP address. In this case, I pretend to be IP address 101, 101, 101, 101, performing VRF hopping, sending this pre-encapsulated MPLS traffic onto R4. You see the request as being captured on the interface between R4 and the provider edge device. So when the R4 device takes these packets, inspects the source IP address, it sees that the source IP address has been set to 101, 101, 101, 101. And because this 101 IP address is somewhere on the internet, because it's a public IP, it assumes that it's safe to send the response back onto the internet-connected link. So basically, that's the way we achieve some sort of two-way communication, by only triggering it initially from an MPLS-facing interface. Now, that was pretty much it about MPLS reconnaissance and VRF hopping. A little bit about hardening the environment now. Disable IPTTL propagation at the edge of the MPLS domain, and disable IPCMP tunneling along the LSB. Disable management protocols and unwanted services on customer-facing interfaces, so basically cutting down the attack surface. And generalized TTL security mechanism is a mechanism that prevents a router from processing certain traffic only based on the TTL value. So basically, by knowing the size of your network, you can safely assume that TTL values outside of a specific range are kind of forged by a customer. And in general, it is recommended to follow the best practices as specified in the security framework for MPLS and GMPLS networks. Now, some general guidelines, not specifically related, not necessarily related to MPLS. You should always assume a presence of some sort of malicious or compromised client. So basically, if you're a service provider, never assume that a client is absolutely safe to connect to. Restrictive access control lists should be in place for all of the LSR devices. As I said, most of the service providers rely on the fact that the MPLS network should not be reachable from the outside world, so they have SSH enabled on every single device without filtering traffic from within the MPLS network. For the purpose of securely accessing LSR devices, it's good to have a management VRF with whitelist for only admin workstations, for example. Secure management protocols, I guess that's absolutely obvious, using SNMP version 3, HTTPS and SSH, as opposed to an SNMP 1 or 2, HTTP and Telnet. Now, the routing protocols and the MPLS signaling protocols should be authenticated. MPLS signaling protocols are the protocols used for distributing label information across the MPLS provider network. Unicast reverse back forwarding is a mechanism, as far as I know, implemented in Cisco devices. This mechanism basically captures attempts for forging source IP addresses, and if a source IP address is never supposed to be seen on a particular interface, IP traffic is discarded. Centralized authentication, authorization, and accounting services, and some sort of centralized logging is highly recommended, if not mandatory. And what I find most useful is having some sort of secure configuration baseline. So basically, when you start configuring your device, you need to come up with a fully assessed configuration, fully hardened configuration, and then replicate this configuration across the devices within the network. You need to keep track of every single change that you make to the configuration file, and basically you need to approve every single change before it is committed in the network. Couple of ideas for future research or building on top of that one. And basically, we need some sort of improvement for the VRF hopping attack scenarios, because as you can see, right now we rely on either a misconfigured device or some sort of poorly designed network. We need to explore some other UDP protocols that may be abused remotely without having misconfigurations. Interesting topic to look at is MPLS signaling protocols. As I mentioned, these are the protocols that are used to kind of sync the label information basis for the LSR devices. And again, fuzzing is always an option. I think I found just a couple of bugs by basic fuzzing using Sully L2. So having a proper MPLS fuzzer and MPLS related protocols fuzzer is definitely something to look at in the future. Couple of acknowledgements. I want to thank a bunch of guys from MWR Labs for giving me the opportunity of testing an MPLS production network. I want to thank Pavel Stefanov, really good friend of mine, for kind of helping me with various MPLS setups that I had to build before pen testing them. So that was pretty much it. If you have any questions, I'm happy to take them now, or maybe drop me sometime later.
So in your spoofed packets for VRF hopping and the ICMP packets that actually got the echo replies back, are you just putting additional MPLS header when normally you would not have it?
Yeah, exactly.
And put the labels from 1000 to 1500 and send 500 packets?
Yeah, that's exactly it. So basically, in certain cases, a provider edge device would not process pre-encapsulated ICMP, pre-encapsulated in MPLS ICMP traffic. But a bunch of vendors were found to having MPLS globally enabled and not having the option of disabling MPLS on a particular interface. So by default, a client, when generating an ICMP ECK request, it would send it encapsulated in IP. But for this attack to work, you can encapsulate this IP, encapsulating ICMP, encapsulate the whole thing in MPLS, and relying on the fact that a bunch of vendors are affected by this and would process the MPLS traffic on an IP interface. So yeah, that's how it works.
Okay, and the status of research is that some injection is possible, but there is no research on leaking from other VRF, right?
Again?
So you succeeded putting some traffic from VRF A to VRF B, but was there any possibility of like sniffing packets?
Yeah, you're right. So, yeah, I got the question. So yeah, there was no way, I found no way to kind of leak traffic outside of a VRF, or in most of the cases, even get a response back. So this is exactly the equivalent of VLAN hopping. Most of the time, if you don't have a misconfigured network or a poorly designed network, you will never receive the request back.
Okay, all right, thank you. That's it.
How did Jay speak into this? Oh my God, this is so cool. Any in the wild scenarios where this happened, where attackers were caught doing that or trying to infiltrate an MPLS provider to misconfigure the...
Not as far as I know. And I guess for most of the attackers, it would be easier to kind of break in the data center and get physical connectivity to the network. But as far as I know, there haven't been any vulnerabilities published right until I reported some of these. So caught in the wild, probably safely to assume no.
Actually, I would like to answer to previous question because we had once almost the same work project to test a network with MPLS subsystem, something like that, and actually we successfully attacked MPLS core network and got access into it. Yes, but we used I don't know common ways to hack something like.
So it was not an issue with an MPLS configuration, but rather that kind of
configuration of devices. Yeah, but if we would know this information that you told us today, it would be really useful for us. So thank you.
Thanks. It would be nice to have a chat anyway.
Yeah.
Okay, thanks guys.